Hello everybody, I'm Sylvain de Rossi. I work in MRI, which is a microscopy facility in Montpellier, south of France. This facility is a multi-site of UMS Biocampus, member of the National Infrastructure of France-BioImaging. MRI offers equipment and expertise in light and electron microscopy, screening, or X-tomography and flow cytometry, as well as in image analysis and software development to support you in your scientific project in life biology. In this video, I will present you the MuviSPIM from Luxendo Brugger. This system was originally developed by Lars Hufnagel at EMBL. A startup was born as a result of this project to market the prototype and make it a turnkey system. The company presents several microscope setups, all based around light sheet technology. This is what the machine looks like. So it is a SPIM geometry with an optical bench placed horizontally. The major feature of this setup is two-sided excitation arms called backsheet and frontsheet, combined with two-sided detection arm called left and right side, associated with two cameras. In the middle, we've got an octagon, which is a combination of four water objectives, 210x plus 220x. The sample is mounted from below by a specific sample holder. As I already said, we've got two 10x for illumination that gives us a thickness of light sheet less than 3 micron. For detection, we've got 220x with a high numerical aperture of 1.0 given very bright images. All of these objectives are water dipping. We have a final magnification around 33, which is a combination between a 20x objective detection and a 300mm tube lens. We can manually change this tube lens in order to get a magnification of 20x. Sample is moving by 3 motors to move in the 3 directions of space, plus the rotation. Images are done by 2 SCMOS cameras from Hamamatsu, which is a very sensitive sensor with a quantum efficiency around 80% combined with a small pixel size of 6.5 micron. With the magnification at 33, the field of view we get is around 400 micron by 400 micron. This camera has also a rolling shutter mode that is very useful to improve image quality. We'll see later what it is and how does it works. Both light sheets are treated by a DSLM, digital scan laser light sheet, which allows to obtain a clean sheet of light. Why such a 4-lens configuration? What is the main interest for imaging? To understand, let's take a closer look at how a classic geometry with 2 objectives works. The major drawback of such a setup is that it creates images that are inhomogeneous, and this is due by the illumination. In fact, light is absorbed by the sample itself, which reduces the efficiency of excitation of the right side of the sample, resulting in an inhomogeneous and degraded images in this part. To overcome this issue, we can superimpose a second light sheet coming from the other direction, so as to maximize the excitation of the right part of the sample. So now we have an homogeneous illumination given a much better image. Now, let's image this tag of our sample in order to build a 3D reconstruction. In general, in light sheet microscopy, the sample is moving in the 3 directions of space in order to let the optical system as static as possible, which is much better to keep a clean sheet. When we can scan the sample in Z, for example, we start from the bottom. In this configuration, the fluorescence light has a short run distance in the sample before to reach the objective. In this case, scattering phenomena and absorptions are minimizing. But the more go up in the sample, the more these phenomena increase drastically. The overall quality of images is affected. The signal-to-noise ratio decreases sharply. which once again creates inhomogeneous images. To overcome this issue, a second detection objective can be used to optimize the detection of the upper part of the sample. So we end up with two stacks of images that have to be fused to keep only the best parts of them. We will talk more about this in the video regarding image analysis. With this system, in one pass, a single Z-stack results in a homogeneous stack of images regarding illumination and detection. With this four-axis concept, the MuviSPIM provides high-quality images with a high signal-to-noise ratio. This unique geometry provides four orthogonal views of the specimen without the need for sample rotation, avoiding shadowing effect and facilitating long-term imaging. So where does stripping artifacts come from? Actually, this is due to absorption of light by dark or dense object. This produces a shadow along the excitation profile. The second excitation arm allows to correct this effect if the sample is not too scattering. But these artifacts are completely reduced by multi-views imaging regardless of scattering, or how dense is the sample. For other light sheets like the Z1 from Zeiss, a pivot scan is used to average these artifacts and thus make them disappear. But this requires several passes of the sheet on the sample, thus increasing the bleaching. A second advantage of this setup is the line mode. This acquisition mode uses the camera's rolling shutter that allows a synchronization between the Gaussian beam scanning and camera reading. In normal operating mode, all pixels are active during the scan beam. This implies that the scattered photon can end up on any part of the sensor and considerably reduces the signal-to-noise ratio. This is especially noticeable on fixed samples. The sheet of light is swept in very precise synchronization to the rolling shutter of the camera. By using this combination of illumination and camera rollout, very fast acquisition of optically sectioned image is enabled. Additionally, there is significantly reduced photobleaching and phototoxicity to the sample as compared to many other methods. This synchronization needs a calibration that we'll see later in a specific video. Results obtained with Drosophila embryo that are known like sample very diffusing are pretty impressive. We can easily see the gain in terms of signal-to-noise ratio. Haze has completely disappeared. In this video, I want to show you how we prepare sample holder adapted for Drosophila embryo. For this, we need glass capillaries. You can see references in the screen. A tool specially designed to hold them securely in order to cut them to the correct size. I use a specific pen for this. I collect 4 of them and place them in this tool to cut them to the size of 3.7 cm. With a few strokes of this pen at different places around the capillaries, we will be able to simply break them without creating breaks with a cut as clean as possible. For this step, I need a clamp, a scissor, a metal tip with a cone of about 70 degrees to make a footprint in my agarose gem. I also need this gutter tool that allows me to effectively keep my capillary filled with agarose while I install the metal tip. Now, I cut a piece of this electric cable to a size slightly larger than the size of my capillary. The diameter of this cable should be as close as possible to the inner diameter of the glass capillary. Here it is a 1 mm diameter wire. It is important to have a perfect fit
of this cable because it will allow my agarose gel to be set up. I collect my agarose in an aliquot at a temperature of about 60 degrees to keep it liquid. I suck the agarose into my capillary by gently pulling the cable out. I put the capillary in the guide provided for this purpose. Then I place my metal tip in this same guide, which I gently push into my capillary filled with agarose, allowing out air bubbles. 30 minutes later, the agarose has solidified and I can gently remove the tip. You can see under a binocular the footprint created by the metal cone. Then I have to fill the well with water or PBS in our case. To do this, I put the capillary in a falcon filled with the desired solution, and I shake everything with a vortex, which will allow the air stuck in the well to be replaced by liquid. In this part, I will show you how to put a Drosophila embryo in our capillary. First of all, you have to decorionate the eggs. To collect them, you must first take them from the culture dish using a brush. A small benchtop binocular is used for this. The egg is placed on a piece of tape on a glass slide to hold it during the decorionating process. This step is done using another piece of double-sided tape. Using the tip of the tape, gently roll the embryo to remove the chorion. This step is done very easily. The most delicate part is the introduction of the embryo into the capillary, and this is what requires the most know-how. First, the embryo is collected using a glass capillary. By just placing the glass tip on the sample, it immediately adheres to it. The thinner your glass tip, the better the transfer will be. Once the embryo is on the surface of the liquid, because the embryo is floating, you must push it to the bottom of the well. This requires the greatest forwardness in order to not crush the embryo on glass edges. Then, we push agarose gel out of the capillary as we cannot image through it. It will introduce too many aberrations on the sheets due to the mismatch of refractive index. You can notice a second black dot in the well. It is undoubtedly a dust brought by the various manipulations. All of these steps require great care and also a lot of cleanliness, otherwise debris will be imaged, which will greatly disrupt the imagery of our object of interest. In this video, I will show you how to visualize light sheets through the software. To see them on the cameras, you just have to fill the water tank, use the 488 laser and combine it with a long pass filter at 561 nanometers. This way, you can easily visualize beams in the camera's field of view. Here there are two beams corresponding to two illumination arms, the front side and the back side illumination. If I block the front side beam, I only visualize the beam coming from the back arm. Here we are not directly visualizing the sheet, but the non-scan excitation beams. We use the so-called park mode. We look at the geometry of the Gaussian beam's laser, giving us an idea of the beam thickness and hence the axial resolution of our SPIM. But at this moment, we are not really focused. So first of all, we have to adjust the beam focus in a dedicated window. Step by step, we focus the beam in the focus plane of our objective. Secondly, with the help of the offset, the beam has to be aligned in the middle of the camera field. If necessary, the beam tilt will be readjusted with a screwdriver to move a mirror directly on the optical bench. If the beam is not perfectly focused on both cameras, we can slightly rework on one of the objectives to offset this shift. Here, we slightly press the right objective's head. Once the back beam aligned, we do the same on the front one, blocking the other beam, adjusting its focus with the offset to center it, and adjusting its tilt if it is appropriate. We can then visualize the two beams in the camera's field. Both have to overlay along the propagation axis. We can notice that in our case, the two wastes are not overlaying. Hence, we don't have the best configuration to get the thinnest sheets, but a trade-off to get the correct thickness of sheet on a more important distance. On this picture, case 1, there is a quasi-overlay of the beams. That leads to an excitation sheet as thin as possible to get the best axial resolution that we can obtain. In the case 2, a shift between both beams gives less sharpness with a sheet moderately thicker than the previous one, but with a more important length of focus. So now let's go to the scanner calibration. This step is necessary if we want to use the line mode. For this, we launch a specific wizard. One beam is automatically switched off. A blue line indicates the automatic beam detection by software. If this blue line is not overlaid perfectly over the Gaussian beam, we repeat the sequence until to superimpose them. A clean beam is necessary to succeed this test. This step is done 3 times at least to get the perfect synchronization between scan beam and readout cameras. Once alignment done, all that remains is to put the sample in place and image it. In this video, I want to briefly show you the acquisition software we use. My Drosophila embryo have a nucleus labeling. To image it, I need a 561 laser for excitation, coupled to a long-pass filter at 561 nanometers. So let's start the live mode in order to find the embryo. We have to locate the sample by moving the capillary in the 3 directions of space. We can manage display by modifying the histogram for each cameras. We can also operate the line mode in order to remove scattering photons. We can already see a big difference regarding the image quality on each camera. The left one is worse than the right one. This is due to the fact that at this moment the fluorescence photons coming from this layer have a longer distance to do in the sample before to reach the left objective. In the middle of the embryo, image quality should be approximately the same for both cameras. In the upper part of each camera, we can see a dust causing a shadowing effect. We can also observe in a less obvious way the nucleus themselves create these stripping artifacts. To open my HDF file images, I commonly use Fiji with the plugin Big Data Processor 2, developed by Christian Tischer. This plugin is really easy to use for an interactive processing of terabyte-sized image data. This plugin is based on a lazy loading and lazy computation. It means that only the currently viewed image plane is processed. A complete data browsing, data selection, and data processing workflow can be configured in a few minutes, even for terabyte-sized image data. Here, I open the left camera and the right one, and play with the Z-slicer. If I add a time series, it would be easy to manage both time and Z in a fluent manner. To quickly have an overview of my experiments, it seems to be a good tool. So now, I want to show you how to fuse both images in order to have a unique stack with the best parts of them. For this, I use a software developed by Luxendo, which gives us the possibility to fuse our 2 stacks coming from our 2 cameras. We can use 2 ways. The first one uses a method based on beads registration, and the second one without beads. This is the solution I choose to show you in this video. So here we just need to calibrate images by giving the whole magnification of the system and the pixel size. We have different parameters to set here that I don't explain until to launch the fusion process. The speed processing is really depending on the computer in terms of CPU, GPU. We need time, even for a dedicated computer. If I open the stack on Fiji, I can quickly evaluate the result and clearly see that this final fused stack is composed by the best part of the two original stacks. It is also possible to deconvolve light sheet images by using, for example, Huygens professional software. This software is opening the H-file format coming from the MuviSPIM, so it's very practical. We don't need to previously convert our data. Metadata are not recognized, so users have to set some parameters like the pixel size in X, Y, and Z direction, the type of the detection objective, its magnification, the number of sheets, and if we are using 1 or 2 photon excitation. We also have to set the emission and excitation wavelength, the thickness of our sheets, and so on. When it's done, we can launch the deconvolution process. We set the background correction, choose different algorithms, set the number of iterations, evaluate the signal-to-noise ratio, and other parameters like the bleaching correction. The speed of process is dependent of the graphic card because Huygens use GPU to accelerate the calculation. We can see the improvement of this deconvolution directly in the viewer of Huygens Professional. To visualize the 3D rendering, we commonly use images from BitPlane. Before to open the data, we have to convert in IMS format with a specific converter. When it's done, you directly drag and drop your IMS files in images to visualize it in 3D. Here, I'm just changing the lookup table in gray. Then, with the 3D viewer, I manipulate my sample in all directions of space. Here again, we need a powerful computer. Specific recommendations are available in the BitPlane website.
So now, let's talking about a few applications we have in the facility. The first example I would like to show you is the Drosophila embryo development. In this video, we can see the dorsal and the ventral views of a maximum intensity projected Z stacks. Both views are imaged in the same time by two cameras. In magenta, we have nucleus and in green, RNA transcription sites. Light sheet allows to watch from earlier development to late development state with very low phototoxicity, keeping the embryo alive. To give you an idea of the very low phototoxicity given by this light sheet, you have to know that we need more than 200,000 slices to do this movie, resulting of 230 slices in Z for 2 colors every 2 minutes during 15 hours. So now, let's talking about a few applications we have in the facility. The first example I would like to show you is the Drosophila embryo development. In this video, we can see the dorsal and the ventral views of a maximum intensity projected Z stacks. Both views are imaged in the same time by two cameras. In magenta, we have nucleus and in green, RNA transcription sites. Light sheet allows to watch from earlier development to late development state with very low phototoxicity, keeping the embryo alive. To give you an idea of the very low phototoxicity given by this light sheet, you have to know that we need more than 200,000 slices to do this movie, resulting of 230 slices in Z for 2 colors every 2 minutes during 15 hours. It's also possible to image plants like Arabidopsis thaliana, and more particularly, secondary root growing. For this, we need a specific mounting by using FEP tube. This time-lapse has been done by Karine Alcon from BPMP over 16 hours with an acquisition every 15 minutes. To maintain the sample alive during this long period, we build a homemade LED illumination using Arduino in order to simulate sunlight and facilitate the root growing. In this example, I choose to illustrate the speed and the low phototoxicity we can get with the MuVi. At the CRBM Institute, Patrick Lemaire's lab worked, among other things, on development of marine organisms, like Phallusia mamillata, from the very earliest state to the wool larva. For this, they need to acquire 4 stacks of 200 slices each as fast as possible, and this every 2 minutes in order to follow precisely the fate of each cell. The 4 views are necessary in order to improve the reconstruction. As you can see here, after the fusion processing, we optimize membrane signal, which facilitates the segmentation process. After fusion and segmentation, they use a homemade software. The 3D rendering you can see in this video has been done with Morphonet. Click the link below to learn more about this browser. So Morphonet is a novel concept of web-based morphodynamic browser. It is an interactive anatomical browser for 3D plus time segmented datasets. It provides a comprehensive palette of interaction tools to explore the structure, dynamics, and variability of biological shapes, from fossils to developing embryos. To conclude, I would say that this microscope, the MuviSPIM, is a good setup to image medium sample in live. Live sheet approach offers a very low phototoxicity associated with water dipping objectives, which are very bright due to their high numerical aperture. It permits to reach a cellular resolution at a very high rate imaging. The line mode and multi-view imaging are respectively a very useful tools to deblur images and improve a lot the signal-to-noise ratio. The one I presented today is not up to date, and I invite you to look at the Bruker website to learn more about MuviSPIM family. Some of them allows photomanipulation to do FRAP or photoablation. They propose a so-called flexible light sheet that permits to play with the thickness of beams, thereby play with resolution. They also developed a specific octagon dedicated for cleared sample. One of the more important drawbacks, not necessarily linked to this microscope, depending on all light sheet technologies, is the data management. You have to be aware that fast live imaging on fixed sample generates a huge amount of data, from gigabyte to terabyte. Quantify, visualize, or even manipulate or transfer this data is challenging. If I could advise you, I would insist in these points. The network has to be adapted for transferring data as quick as possible. I will choose at least a 10 gigabyte network. A specific analysis computer has to be dedicated for visualization and quantification. Of course, you need strong CPU with multi-core or a big quantity of RAM, a powerful graphic card, but in my point of view, the bottleneck is hard disk and their capabilities to read and write your data. And then you have to be carefully about softwares. Some of them are terabyte compatible, some are using GPU, some need cache, and so on. Most of the time, suppliers' recommendations are available for each software, whether for open source or private company. To conclude, I would like to thank my colleagues from the facility. I also wanted to acknowledge Jérémy Dufour from Mounia Laga's lab at the IGMM Institute of Montpellier for giving us Drosophila embryos, and Patrick Lemaire and the Bettencourt Foundation for funding the MuviSPIM and open his access to the whole community. I also thank all the people involved in the FBI working group. Thank you for your attention.